It is a pleasure to be back on a campus that I've been to many times in my former life, and I've had a wonderful time interacting with faculty and students for the last few hours. When I was here last speaking in public some 2.5 years ago, I did talk about energy and tried, as I try to do now in my current job, to do a good fact-based analysis of what the problems are and what we need to be doing. But I've come to realize in the last year or so that energy is one piece, a big piece, but only one piece of a much broader set of problems that go under the sustainability rubric. And that these are, in fact, a very severe set of challenges that we will face in the next several, we are facing already, but will become exacerbated in the next several decades. And so I'd like to offer some thoughts today on that topic. We will talk about energy some, but also about other sustainability issues. Consistent with my training as a theoretical physicist, I'm going to try to keep the discussion relatively simple, fact-based, look at the big trends and the big picture, and not get too bogged down in the details, since it's kind of hard to predict the details in a subject that's a complicated mix of technology, economics, politics, et cetera. Also, I should remark that this is only the second public outing for much of this material, and so I very much look forward to the Q&A session and hope, as usual, to just iteratively improve the presentation so it just keeps getting better. Okay, I think the main points can be summarized in two theses. The first is that global development and population growth, the combination of these two, will place unprecedented stresses on resources. And this I call the sustainability problem with the big S sustainability problem. But there is also a second problem, the little s sustainability problem, and that is that these same factors will have a profound influence on U.S. domestic and global circumstances. And it is the combination, and by the way, one could say the same in the second bullet about the EU or other parts of the developed world. And it is the navigation of these changes that will be the major task confronting us in the next several decades. So I'd now like to go through a talk in 4 sections, talk a little bit about the global drivers quantitatively, talk about the big S sustainability in the context of energy, some brief remarks about the big S sustainability in the context of food and water and the relationship between these dimensions, and then close with some thoughts on the little s sustainability problem. Global drivers. So this is one of my favorite charts to talk about energy and it shows the consumption per capita of energy in a given year plotted against the GDP per capita in constant dollars for various countries. There are many things you can learn from this chart, but the broad features are that there is a high but relatively slowly growing consumption of energy in the developed world, and that there is a small but rapidly growing consumption of energy in the developing world. And that as those countries in the developing world develop, there is every expectation that their energy demand will increase per capita. The other big picture takeaway from this chart is that there are no negative slopes on this chart. Nobody has succeeded yet in using less energy as they've gotten richer per capita. That same pattern of consumption follows for other things with development. This shows the per capita consumption of calories per day against GDP, different snapshots each year for different countries. There are some outliers, interestingly, Japan and South Korea, but by and large, there is a general trend that consumption increases with GDP or development. The same is true for subcategories of that. This is meat consumption on a log-log scale. When people get richer, not surprisingly, they seem to prefer eating meat. Okay. Calories also increase with time. This is the food. We can plot many other things, but just to show you that historically, at least as development has proceeded, consumption has gone up. This shows the world's growth in calorie consumption per capita over the last 50 or 60 years. You can see it goes up, and it's mainly due to the increase in the developing countries. So we have a circumstance that at least historically, consumption has gone up universally and monotonically with development. The second driver is the world's population. We are a little bit more in 2010, a little bit more than halfway through an unprecedented quadrupling of the world's population from 1950 to 2050, as shown by this graph. You can see that most of the growth is in the lower two segments of each bar in Asia and Africa, and that the population of the developed world is, and is projected to be with good confidence, relatively constant out to the middle of this century. Of these two circumstances, population growth and the increase in consumption with development, one can draw some rather simple but I think profound conclusions. Let us take the US as a benchmark. The US is 4% of the world's people, and roughly, in round numbers, 20% of its consumption. We're also 20% of the world's GDP in round numbers. And you can see here different quantities that show that. Here's the population, 4.5%, GDP, 20%, oil consumption, well, 23%, gas, 20%, and so on. Number of nuclear power plants, we have about a quarter. In round numbers, the US is a quarter of the world with 4% of its population. There are some interesting anomalies. Not much steel or concrete, largely because we've been finished building our infrastructure, whereas the developing world is doing that. That circumstance, this imbalance, impacts both the global resource issue, the big S problem, and the little s problem. And so let me continue on the big S problem for a while. Let's just do a little bit of math, simple math. If we take the current US consumption as 20% of the world, divide by the 0.3 billion people that are in the US, we get a US per capita consumption of 0.7 of the current per billion. Now, it's unlikely that in the next 40 years the whole world is going to reach the US level of development or consumption, but just as an upper limit, let's suppose that they do. If 7 billion people consume at the US consumption rate, we're going to use 5 times the current resources that we're using now every day. The 9 billion people by the middle of the century at the same rate would consume 6 times the current resources. You say, well, the Europeans do better than we do. Let's use Europe as a benchmark. These numbers come down by about 30%. So instead of 6 times current by mid-century, we're at 4 times current by mid-century. Given that the world is already in many cases at a breaking point in terms of resource consumption, this is not a happy picture. Of course, this is an old story. Malthus realized this in 1789. The perpetual tendency to increase beyond the means of subsistence is one of the general laws of animated nature, which we can have no reason to expect to change. Of course, it did not happen in Malthus's time, in the 200 and some odd years since. So the question is it different this time? And maybe there is reason to expect it might be different. Certainly the scale and rate of growth is different this time than it ever has been before. The resource intensity of modern developed societies is much greater now than it has been in the last 200 and some odd years. And also, the Earth is in fact finite, and we are starting to understand what the limits of the Earth's carrying capacity are. And so I look at this and realize that there are, in fact, only 3 possible resolutions here. One is that we learn to decouple development and consumption. We learn how to conserve, to make do with using less, and that conservation is enabled, of course, by policy and technology. We can find new or substitute resources for those that we're using now. Or the third is that we can reset expectations and restrain development. Restraining development doesn't necessarily mean less development, but it might mean that some of the countries do it slower and smarter than they're doing it now, and that we in the developed world exercise greater wisdom in building our infrastructure and in the way that we behave. These are, of course, not exclusive alternatives. We're going to see some combination of both, or all three, and the outcome will depend, as it always does, on policy, economy, and technology. So that's the big picture. Let me now focus in on the energy dimension of sustainability. This is the projection of the world's primary energy use from the present 2010 going out to 2030. You can see it's split up into the OECD countries, the developed world, and the non-OECD countries, the rest of the world. Right now, there's a roughly 50-50 balance in consumption, but the development of the developing world and the growth in population drive a 44% increase in global energy use under business as usual, or the reference scenario as it's called, and that 82% of that increase occurs in the developing world, as you can see by the large bit of the red bar at the end compared to the blue bar. California. It's interesting to see where California sits in all of this, and I dug out some numbers. The blue curve on top, the top blue curve up here, shows the per capita consumption of energy in California from 1977 up through the present. And you can see that the state did manage to reduce its per capita energy consumption from 1977 up to about 1989 or so by about, what is that, something like 15%. But since 1990, it has been essentially constant. Why did that happen? Well, it's interesting if you look at the blue line, which shows the energy use per capita in California without petroleum, not oil and gas, and you can see that that's essentially constant. And so this decrease in energy use over here was associated with the oil shock in the late 70s. We got oil out of power, and we made some improvement in the efficiency of automobiles. But since 1990, essentially constant per capita use, of course growing energy use in the state because the population has been going up. At the same time, it's great that the GDP per capita, which is shown on the red graph, has gone up significantly over the last 40 years, 35 years, wonderful. Of course, we have seen many changes in California's economy, including a fall off in manufacturing in this state, which helps keep the energy use down as the economy grows. Just for reference, the U.S. numbers currently, California is 240 million BTUs per person. The U.S. average is about 350 or 340, so California is more energy efficient. Again, you can blame it in part on policies and in part on the nature of our economy and climate. And also the state is relatively richer. U.S. per capita GDP is about 36,000 a year, and as you see here, California currently is about 42. Going out, reasonable projections of the reference case going out. Where is the world going to get its energy? Right now, about 80% of the world's primary energy comes from fossil fuels, and that mix is not going to change very much going out to 2030 unless something dramatic happens. You can see that renewables are the fastest growing component of this mix, but even out to 2030, they're only 11% of the primary energy use. Well, if we're running on fossil fuels, is the world going to run out? The answer is no. We have ample reserves of oil in the ground. There are some discussions, of course, of oil running out. But in fact, that's simply, I think, a misterminology between the geologists who are trained to go out and look for oil that flows and the economists who think about oil as all sorts. And if the world ever started to feel like it was running out of oil and still needed oil, there are many unconventional reserves that one can go to. Natural gas, this chart is a little old. The world has 60, 70 years of natural gas right now that it knows to get out of the ground. The U.S. has recently opened up vast amounts of so-called tight gas and shale gas that are not accounted for here yet. In fact, that's a domestic resource that would provide perhaps up to several hundred years' worth of natural gas for the U.S. at current consumption rates. And coal, plenty of coal in the ground, hundreds of years of coal in the big demand centers in the US and in China. Just a bit about the ongoing energy mix going forward. This shows nuclear power in the recent past, projected near future, and out to 2030. Most of the increase in nuclear power is projected to be in China and India. This country hasn't built a new nuclear plant in 30 years. China and India are each building plants at the rate of about 2 a year, and you can see the corresponding shift in balance as we go forward. For example, the purple bar here showing China increases enormously. North America, slight increase going forward. Renewables, wind and water power, again in the OECD and non-OECD, you can see that the biggest growth in the next several decades will be in hydroelectric. Wind will grow as a fraction strongly. We might get to 20% wind by 2030 in this country, and other renewables, solar, tidal, biomass, growing, but still a small fraction of the total. So what's the problem? If we've got plenty of energy resource, build nuclear power plants, wind, fossil fuels, what are the problems? There are 3 problems. One is energy poverty. There are about 2 billion people in the world who do not have even enough energy for the barest standard of living, cooking, lighting, heat. And the sad part is that we could fix the problems for those folks without impacting much of the energy situation generated by the people in the rest of the world. The second problem is energy security. There is an imbalance in the geographical distribution of resources, particularly liquid hydrocarbons, but also natural gas for Europe and Japan. And then finally, there are greenhouse gas emissions. We are significantly perturbing the global carbon cycle and with it endangering the climate system. Let me talk a word about each of these latter 2 problems and tell you what we're doing about it. The distribution of crude reserves. This shows who's got the reserves of conventional oil around the world. You can see OPEC is holding 80–90% of the conventional reserves. They account for only 40% of the global supply. This renders the energy security of the United States and other consuming countries subject to the decisions and fortunes of countries whose actions may not be as transparent as we would like, and whose futures may not be as stable as we would like. Currently, the U.S. is spending about $400 billion a year on importing 12 million barrels a day of oil at $80 a barrel. And that is a fair chunk of change, $400 billion, right? Half a stimulus, for example. In recognition of that issue of energy security, the administration has set a goal of, by 2020, reducing oil use by 3.5 million barrels a day, which is roughly 1/4 of what we use for transportation every day in this country. How are we going to do that? The first step is to increase the efficiency of vehicles, and the CAFE standards that drive the efficiency of new vehicles are increasing now from the current 27 miles per gallon to 35 miles per gallon by 2016. And there's plenty of technical headroom to go to 42 miles a gallon, as the Europeans are now at. So the first thing is increase CAFE standards. The second thing to do is to improve the internal combustion engine. Although we will eventually power our transportation perhaps differently, there is plenty of technical headroom in improving the internal combustion engine, and is the fastest way to induce efficiency. There are technologies like homogeneous charge compression, ignition, variable valve timing, exhaust gas recycling, all of which exist or almost exist and are being deployed in high-end vehicles, and we need the drive to move them into the mass market. The third thing we need to do is to promote the gradual electrification of the transportation system. There is a sequence of technologies from the ordinary internal combustion engine through hybrids to plug-in hybrids to full battery vehicles. We need to be marching down that sequence at a pace determined by how well we can build batteries and how cheaply we can do that. And then finally, we need to be working on alternative fuels, beyond those derived from fossil carbon. Second, third generation biofuels are an obvious target. They can scale. We need to make them economic. And I'm pleased to say that the administration is pushing on all of those fronts, quite hard, actually. And I think we're going to see a significant reduction in oil use going forward over the next decade. The second problem is greenhouse gas emissions. This shows energy-related greenhouse gas emissions, CO2, from 2006 to the next 20 years. And again, you can see most of the growth is in the developing world. Hence, the need both to engage the developing world to try to restrain their emissions, but also in this country to reduce our own emissions, both to contribute directly to solving the problem, to lead the world in taking action on this problem, and frankly also to develop the technologies that are going to be important in solving this problem so that the United States can reap some of the economic benefit of developing and producing those technologies. So that is pretty much the energy scene. Let me not go through this chart. Let me now shift to two other dimensions of sustainability, water and food, talk a little bit about each of them and the interconnection with energy, and then try to draw some general conclusions. Water. We have seen the demand for water is increasing. Agriculture, energy is a big user of water. Right now, households in developed countries use 6 times the water use in developing countries. And of course, the water system will be exacerbated by climate change. While the changes in the climate in California over the last decade or two are not directly attributable to greenhouse gases with any confidence, certainly the fact that the climate is changing shows us what the impact could be on water situations here in California. Like the energy problem, there is plenty of water. The issue with water is the quality, the timing of the water, given snow melts, and the geographical dislocation of where the water is. Also of interest and a problem is the depletion of stored water in the aquifers. And it's important to bear in mind that water is not a global commodity like oil and gas. It's very much local. And generally, we do not do long-distance transportation of water. And so water really devolves into a set of more or less local or regional problems. On the issue of whether there is plenty of water, of the world's total resources, 2.5% is in fresh water. Of that, in fresh water, 0.4% is in the surface and atmosphere. And of that water, most of it is in freshwater lakes and some is in the rivers. If we take that water and ask how is it used, you can see that almost all of it is used in agriculture, and domestic and industrial use accounts for less than 10% globally. So we use mostly water to grow our food, and frankly, again, not very efficiently. If you look around the world at where different regions use water in different ways, again, you can see the dominance of agriculture, except in Europe, and the relatively small amounts of industrial and domestic, except in Europe and North America, where a lot of that industrial use is for power generation. One projection of climate change out to 2050 in a model, you can see generally a strong drying, reduction in precipitation and runoff in the subtropical regions, enhancement in some places, but by and large, where people are living in Europe, North America, the Southwest, as you can see, Southern Africa, strong drying. So that is the rough picture with water. Let me talk about food a little bit. We've already seen that food is rising with development in terms of demand. There's the increase in quality, the shift from crops to animal proteins, and of course the obvious question, first of all, is can we grow enough food? My own sense is probably yes. This shows the land use around the globe, and you can see that right now we use only 5% of the land to grow cereals, another 7% to grow other crops, some for pasture and range. A lot of the world not used for those intensive food production activities. There is plenty of land. The question is, can we develop the technologies to grow food on those lands? Animal protein production is rising. You can see, again, vast increases in production of pork, poultry, and farm fish over the last 50 years or so. Some of the choices for what people produce and what they consume are governed by economics. This shows the annual global agricultural economy, about $200 billion, as shown up there on the top. Roughly half of that revenue, $104 billion, comes from the production of livestock. And so it's no accident that we're producing a lot of livestock, because it's a pretty lucrative business. On the other hand, it's also what people demand traditionally as they've gotten richer. Food yield changes to 2050. Again, climate change is not friendly to agricultural production. One can always shift agricultural production, but that's not so easy to do in the developing world or undeveloped world. Fairly easy to do, I think, in the developed world, although not without its stresses. This nexus of food, water, and energy is a very complicated one that's sensitive to climate. We use water for power production, and we have already seen in recent years the need to curtail power production in some plants simply because the water is not available or because the intake water is too warm and the plant can't run thermally efficiently. We use power to move water. Some surprisingly large fraction of California's energy, I think 15% of its electricity, is used to move water around the state. That's not very smart. Obviously, food and biofuels or biomass for power are intimately connected, since we can only grow so much. We need energy and water for agriculture, as I've shown you, and agriculture and land use, particularly deforestation, interact with the climate. So there is a real nexus here of complicated issues to try to sort out. It's interesting, just back on water use again, more water is used for food and electricity production than is used directly. And if you look at the scale of what you need for water just for direct consumption in the cities, that's actually a pretty easy problem to solve technically with the energy that we have. It is the energy use, the water use for agriculture that is the real problem. We need to make that much more efficient, and even modest amounts of efficiency gains in agriculture will fix the domestic problem. One other water-food chart. This shows how much water it takes to produce comparable amounts of product. Beef, you can see, is extraordinarily water-intensive, whereas if you go down to soy, you're about a factor of 8 more efficient in terms of water use producing kilogram of product. Okay, so a couple of general lessons to learn from that quick overview of energy, food, and water. There is, or there can be, enough to meet demand. But as we've seen, making that happen is a complicated intertwining of the economic, policy, and social factors. Technology can help in all of this, but is not sufficient. For example, in this country today, we do have the technologies available to meet the administration goal of reducing greenhouse gas emissions by 17% by 2020. More difficult, but possible to hit the 80% goal by 2050. We have those technologies now. They can be made better, but the main barrier is getting them deployed, or at least getting started on deployment. One of the things that can help is a graceful supply curve. I mentioned the oil supply curve. If and when the price of oil goes up, then people start looking at scarcer or more difficult resources to get at, and consequently reserves increase. The same is true for many other natural resources. As long as these supply curves are graceful and you don't suddenly run out of something, they will encourage conservation, the search for new resources, and ultimately substitution of resources. Finally, a lesson maybe most obvious from this energy, water, food nexus is the best policies are not obvious. There are systems effects. Biofuels, food interaction, for example, is an obvious one. And there are diverse interests, and not everybody has the same metric for what a good policy is. The most important thing in all of this is that we inform and educate the general electorate about these issues, and then educate the decision makers so that they can, in fact, try to make wise decisions. And frankly, while I can tell you, and I often do, I can tell you the elevator speech about energy, what the problems are, what technologies, what policies will be effective. It's much harder to tell the elevator speech yet about food or water. We don't have that story down quite, or at least I haven't heard it from very many people. Finally, the trends in all of these sustainability issues are slow to develop and long to fix. I like to use this chart often in my discussions of energy, but I think it's symptomatic of these other problems as well. This shows how the U.S. got its energy supply since 1850. And you can see that at the time of the Civil War it was mostly wood, and in recent decades it's a very interesting mix of wood, supplying the same amount of total energy, by the way, as it did in 1850. But the other sources of energy have grown enormously: coal because of the Industrial Revolution, oil because of the mobility revolution, a little bit of gas, nuclear, and so on. We can change the way in which we do these things, as you can see. On the other hand, the sobering thing about this is it takes decades to change. You can see that nothing happens on the time scale of about 10 years or so, whereas these problems take a long time to develop. And if we get caught short, we're going to have crash programs involved. We are lulled, I think, into energy transformation and thinking it's easier than it's going to be by what we've experienced in information technology, biomedical, and so on. I've taken the last bar on the energy graph here and expanded it for the last 10 years to look at the evolution of personal audio and video technologies. And you can see that at the beginning of the last decade, in 2000, it was all personal CDs and tape players. And now, of course, it's all MP3 and flash. And this transformation of the whole infrastructure happened in less than a decade. But it is a lot harder to move bytes around than it is to move molecules around, as we need to in the energy system. So energy transformation is going to take a long time. It's going to take consistency in policy, in funding. And it's going to take, I think, to accelerate things, a much more interesting and novel set of partnerships between the government, academia, the national labs, and the big and small players in private industry. I don't think we have it sorted out yet. Energy innovation is different, and we're trying various things. Energy frontier research centers, such as one here in UCSB, to work on the underlying science. Innovation hubs that the Department of Energy is just about to stand up that are meant to try to fuse all the players together in a sustained and focused way, together with industry, to quickly transition things out into deployment. We are in the process of standing up 3 hubs this year, one in the conversion of sunlight into fuels, perhaps artificial photosynthesis, a second in the application of modeling and simulation to nuclear power, and the third is in building efficiency. And we hope that these will be a model for a number of other such organizations focused on other high-leverage technologies. We need to worry, and we are worrying about the science and engineering workforce. We have proposals to try to greatly accelerate the training of researchers and the training of energy workers who are going to be needed in order to deploy these things. And then finally, this year, we have also stood up ARPA-E, which is an organization in the Department of Energy meant to fund high-risk transformational research to develop and deploy breakthrough energy technologies. We are seeing, I am told, since I'm new to government, I see a great deal of cooperation among the agencies to try to address these problems, and I'm told it is fairly unprecedented to see this happen in other governments. Okay. What technology, since I'm a technology guy, let me talk a little bit about broadly the things that I think can make a big difference in these sustainability issues. One is biology and biotechnology, especially plants and microbes. The biology is just now starting to really understand how organisms work, genetic code, protein synthesis, function of proteins, regulatory things in cells. Most of that understanding has and rightly will be applied to biomedical issues. On the other hand, plants and microbes are at the base of the food chain, and really microbes in many ways run the world. So can we understand how they really work and harness that functioning in order to do better on these sustainability issues? Just to show you what technology can do, this shows the average yield of corn in the Midwest, Indiana, per acre from 1930 up to 2010, and you can see a dramatic 7-fold increase in productivity due to technologies, genetics, fertilizer, agronomy. Second big one, and as a focus here at UCSB, is material science. Materials, the stuff that everything is made of, catalysts, energy storage materials, membranes, photovoltaics, high leverage things in trying to deal with these problems. We're getting very good at simulating the properties of materials in a computer, predicting them. We're getting very good at being able to synthesize materials to order and characterizing them. And going around that loop faster and faster is going to get us better materials for all of those problems. And then data and understanding. Collection of data is becoming easier, analysis of it, modeling of both physical systems and societal systems. I think in the next several decades are going to let us diagnose, manage, and predict what's happening much better than we can do right now. Okay, 5 minutes or so on the little s problem now, the little s sustainability problem, and then we'll head into Q&A. The world in many ways is unbalanced. This shows, again, the population and GDP imbalances split out into 4 countries, the US, EU, China, and India. Again, you can see the disproportionate GDPs of the US and EU relative to the populations in those countries. Big blue and red here, small blue and red over here, big green, et cetera, right? Good. Compared to the US and the EU, the rest of the world is more numerous. This shows the population numbers between US, EU, China, and India. The rest of the world is hungrier. They're coming up the development curve. It shows the GDP per capita. They are younger on average. Anybody who's been to Asia knows that. Population growth rate for the US is anomalous. Most of that is immigration. The internal population growth rates in the developing world are much greater, as we've seen, and it's developing faster. China's still running at about 9% a year GDP growth, even in the hopefully beginning aftermath of the current economic crisis. US has historically been running at a couple percent a year. So all these folks are moving up, and of course, the rest of the world is just as smart, as we see from the students who come here to this campus and many other campuses in the US from all over the world. Now, you know, one of the things that my physics training has taught me is that nature abhors an imbalance. The second law of thermodynamics, technically stated as entropy always increases. Woody Allen, I think, had a better way of stating it. Namely, nature likes to come into equilibrium. If I take a hot body and a cold body and I put them together, the hot body gets cooler and the cold body gets warmer, and eventually they equilibrate. Similarly, if I have a difference in concentration, salt water and seawater, and I mix them together, they'll all come to some common condition. Simple statements, consequences of the second law. Also from physics, it teaches me that the relaxation, the approach to an equilibrium state can be slowed, for example, by putting a membrane or putting an insulator between the hot and cold bodies. But in general, the greater the imbalance means that the driving force toward equilibrium is greater, and the changes that it involves reaching that equilibrium are more rapid and disruptive. In my mind, sustainability, namely the implications of this imbalance for the US position, or the developed world position, is more about managing imbalances and their relaxation. So the question, obviously, is in a global world with a free flow of capital, free flow of goods, resources, people, the US position of privilege is going to be increasingly difficult to sustain. And I think this implies dramatic shifts in our economic, cultural, and geopolitical heft. The real question is, how will the US respond? Will we go to a Fortress America in which we cut off these flows, insulate ourselves from the rest of the world? Do we accept a position proportional to our population or GDP, whatever that might be? Or do we try to capitalize on the differential advantages that we have to try to realize or at least retard this relaxation and achieve sustainability with a little s? Difficult questions. Here are some trends. This shows U.S. manufacturing starting from 1948 up until more or less the present. You can see that the output of manufacturing as a share of U.S. GDP has been declining steadily over the last 60 years. The fraction of the workforce employed in that activity has also gone down steadily, while the output in real dollars has steadily gone up. Our manufacturing has become more efficient, but we are less dominated by manufacturing in terms of the activities that we do. And of course, our share of global manufacturing has gone down. Manufacturing jobs, this is just data, shows U.S. manufacturing jobs from about the same time period in thousands. Good climb during the post-war years up to 1980, and then a fairly steady decline since 2000, exacerbated, of course, by the current situation, but nevertheless extending certainly over the last decade or so. These are long-term structural shifts in what we do. We have not really been successful in capitalizing on much of the innovation that we do in order to sustain economic activity. This shows worldwide shipments of solar cells. Solar cells were, of course, invented and pioneered here, at least in the commercial level. But you can see that increasingly, up to present, most of the manufacturing is not happening here. It's happening elsewhere. And the U.S. market share has been going down steadily for the last 15 years. There are similar situations in other areas. Fuel-efficient automobiles, we do not dominate that anymore. Batteries, battery manufacturing, we don't dominate that. Electricity transmission, when you look at what China is putting in for its electrical grid, they're about 2 generations ahead of what we're even thinking about doing here. Power electronics, we were discussing this morning, most of that action is happening elsewhere. And nuclear power, as I mentioned, we haven't built a nuclear plant in this country in the last 30 years. The expertise largely resides elsewhere now. So the U.S. in a global context, how do we think about us? We have some differential advantages. The attraction of the American idea. As someone once remarked, the U.S. is perhaps the only country that's founded on an idea and not on the basis of cultural or religious identity. The rule of law, we still do a very good job at that. We have a vibrant innovation system mixing universities, labs, venture capitalists, and big companies. We need to get that going again. Free flow of capital. The capital, of course, flows freely. There's a question of how much capital is available, but at least if we had it, it would flow freely. Protection of IP. This country is very good at that, and great incentives for innovation. And of course, one of the crown jewels in this country, higher education. These are the advantages that we need to nurture and learn how to put together in order to sustain the position of this country. Another issue is that the infrastructure in the U.S. is built. We've built roads, electrical grid, housing over the last 100 and some odd years, whereas in the developing world, it is in the process of being built. And consequently, it is newer and more efficient in the developing world. We need to rebuild ours. And so the skills and capabilities that we need to do this rebuilding are better represented abroad than they are here. This has profound implications for immigration, for labor structure in this country, for how we educate people and in what fields we educate them. And finally, we need to regain favor as a manufacturing venue. If you talk to people who cite large manufacturing facilities, the U.S. Costs of labor, including healthcare, regulatory regimes, financial regimes, are all often more favorable abroad and work against citing large manufacturing facilities here in the U.S. And so we need to fix that. Okay, recap, and then I'll take questions. We've got the two sustainabilities, global development and population growth, affecting resource consumption, availability, unprecedented stresses. And these same factors will have a profound influence on our domestic and global circumstances. And we have perhaps in the last many years started to see that influence. These are complex issues without easy or obvious solutions. But my experience in solving problems is that you first have to name the problem, understand it, and then start to work your way through solutions. And so I think we need to begin, and we've not had much, I think, of a frank conversation about these issues. Be aware of where we're headed and try to understand the implications of the decisions that we make. And as I said at the bottom of the first slide, these issues will be the major task for the next several decades. So thanks for your attention, and I'm happy to take questions or comments.
We focused a lot on efficiency here, as was mentioned in some of the introductions. So there's a difference, and it came out in what you were talking about too, between efficiency and conservation. Yes. I mean, not all efficiency actually leads to conservation.
Right. Indeed.
And it seems to me that efficiency is important, but its principal importance is in the short term, because with growth and so on, it's not going to do it all.
You know, efficiency is a means toward conservation, namely reducing our use of energy, but is unfortunately neither necessary nor sufficient. And you can give many examples where efficiency improvements have not delivered as much as we would hope, or actually have led to increased conservation. My favorite example, for those of you who might find this discussion a little abstract, is computer chips. So we are working very hard to reduce the energy consumption in microprocessors or in memory. And as we do that, what we find is that microprocessors appear everywhere. Rather than using just a limited number of them with less and less energy, we put them more and more places because they are more energy efficient. There are other examples of that so-called rebound effect. And so I think as we develop, there's no reason, and very good reason, why we should be developing and deploying efficiency, but we have to make sure that the policies are in place, whether through regulatory or economic policies, to make sure that we can capture the conservation that those efficiencies can give us.
Yeah. There's a bunch of questions here about different energy technologies, and I think there's enough interest in some of the specifics on these that we might get into them. I think it would be helpful if you could talk a little bit about the current state of play and the future, relatively near future prospects for nuclear reactor technology, and then the increase in energy production from nuclear reactors, how it's going to happen.
So when you look at power generation technologies, electrical power generation, and you try to apply, I think, three essential criteria. One is scalability. Namely, you can imagine a large enough deployment to make a difference. The second is economics, namely that the power production should not break the bank, so to speak. And the third is timeliness, namely that the technology should be available now. When I do that filter, nuclear power comes up pretty high on the list. Remember, nuclear power now supplies 20% of U.S. electricity. We have, as I mentioned several times, not built reactors in this country for a long time. The administration has formally said, the President has said, that nuclear power needs to be a piece of our energy future. I personally would go a little stronger and say if we're going to meet those emissions goals, we're going to need to do more of it. And the administration is, I can tell you, very thoughtful and systematic about how it goes about trying to realize that future, and motion is underway.
Yeah, my reading of a recent NRC report about America's energy future is that, again, in the short term, a lot can be done without actually building new nuclear plants.
Efficiency improvements,
improved technologies,
operating efficiencies, all can be improved. You know, I would say, by the way, that same circumstance of just improving the innards of things applies also to hydropower. We can do a lot by putting modern turbines in some of the existing big hydropower facilities.
Yeah. I'll read this one. Given the enormous potential of solar energy, where's the priority underlined on research and technology for enabling the development of this resource?
Right.
When will this resource become a viable alternative energy relative to what's needed in 2050?
So let me talk about solar photovoltaic first. Right now, it's too expensive, okay, to make a material difference. We are seeing the cost of solar, however, come down dramatically. We're now at, I'm told, about $1 a watt for the cells, photo PV, whereas a few years ago when I started in the business, it was $6 or $7 a watt. So it's coming down. And we need to bring the other parts of the PV system down, the balance of system, so-called inverter, people climbing on your roof, and so on. But it's starting to be viable, particularly here in California, for peak shaving. Large-scale deployments, I think, are going to have to wait as the economics gets better. But it's on the way. We still have a problem with solar in terms of intermittency. We need to worry about energy storage. Can we smooth that load or manage it, manage the intermittent generation capacity? We also have a transmission issue. We need to build the grid out to the sunny places where people don't usually live, the desert, so that we can better capture that sunlight. The other solar technology, which I think is also starting to be viable, and I would say is in the large-scale demonstration phase, is concentrated solar thermal. These are large arrays of mirrors or troughs that capture the sunlight, use it to heat a fluid, and then spin a turbine. We're starting to see some large-scale deployments of that around the country and around the world. So that's cheaper than PV currently, and the technology could be developed further.
Well, one more technology question. It's rather specific but interesting. What's the current status and potential of superconductivity technology in this arena?
Yeah, so superconductivity, I assume we're looking at transmission lines, for example.
Yeah, and actually this question refers to transportation, but I think transmission.
Let me try transmission first. The DOE has supported for many years a high-temperature superconducting power line program. There's a company now that I think the longest power line we've got in existence is of order half a mile on Long Island. It is able to carry high currents with a relatively high power with a relatively small infrastructure. I think we'll first see it in niche applications, places, for example, like Lower Manhattan, where you might want to carry a lot of energy without having big overhead wires. I think we'll be a ways away from large-scale transmission deployment across countries, but across the country. But it is technology we're certainly pushing.
Let me read you two questions because they come at the same thing from very different perspectives. How do you answer the Rupert Murdoch denialists who reject climate change and actively oppose doing anything to limit greenhouse gas loading, I think it says?
Yeah.
Then, your forecasts all assume continued global warming. This is not an assumption supported by the scientific community generally. As yet, it may be that other factors are more important than CO2.
Okay, so boy, several things to say there. I don't think anybody is denying climate change. The whole issue is what the anthropogenic influence is on it. For me, the scientific picture is pretty simple. The carbon dioxide is going up. It's going up because of fossil fuel use and deforestation. We know that unimpeachably. We know that the amounts are such that they should be perturbing the climate system. And we see evidence of that perturbation in many things. It's certainly true, the projections, by the way, not my projections at all, they're some model projections, and they have all of the advantages and all of the drawbacks of model projections, but they give some sense of what is likely to happen. The projections, the climate change is not monotonic. The temperature has not risen in the last decade at anywhere near the rate that it rose in the last 3 decades, say from 1970 to 2000. On the other hand, we have seen many examples in the historical record of slowing down like that. So, for me, it is more a question of risk management and high probabilities. Namely, the CO2 is there. It should be affecting the climate system. We see many signatures already of it. And if the climate system is fluctuating for a while, well, almost certainly it is a fluctuation. And very likely, as the IPCC has said, we will see continued warming in the next many decades.
A very specific question, but I think it relates very much to your overall picture of resource management that you were talking about. How do vegetarian diets influence the global food and energy picture?
Yeah, right.
I mean, you brought up meat,
Yeah,
and
right. So
it's certainly a factor.
I'll preface that by saying that since I was young, I do enjoy a good steak, all right? Well, look, you saw I don't know quantitatively how it works. I haven't worked out those numbers, but you can clearly see that in terms of the resources required to produce 1,000 calories of beef, it's 5-6 times what it takes to produce a comparable amount of grain. So beef is, I think, 7 or 8 times inefficient. Pork is 3 times. Poultry is like 1.2 times or something like that. And for some reason I haven't understood, fish is actually less than 1. But anyway, so there are big differences in the kind of protein you consume, and clearly if the world were vegetarian, we'd probably have a more easy management problem. Again, on the other hand, you have seen the historical and economic patterns of meat consumption, and it's a big behavioral change if we're going to stop eating meat.
Yeah. You didn't talk about this, but, well, I'll read it the way it is. Shouldn't an obvious necessary part of this discussion be population control?
Yeah, population control. So, again, quantitative guy, let's just look at that little bit of math I did for you, the sustainability math. Most of the growth in resource consumption is due to development. The world's population, with fair confidence, will top out at about 9 billion people by 2050 and not get much bigger than that. And so to go from the current 7 to 9 is only 30% effect, whereas the projected growth in consumption due to economic development is much bigger than that. So yes, population is important, particularly in the areas that are growing rapidly. We need to try to manage that stress, but most of the stress is going to be due to development, not population.